So today I'm going to tell you how comprehensive host star characterization can lead to accurate, precise, and physically self-consistent terrestrial planet masses and radii, which then can lead to the best possible insights into their internal structures. I should say that this is a project that was led by two of my former JHU junior colleagues. Alejandro Ross is a JHU undergraduate alumnus who's currently applying to graduate schools, and Enrique Reggiani was formerly a JHU postdoctoral fellow. He's now an assistant or a tenure track assistant astronomer at Morlab. So in our own solar system, we have some insight into the diversity of the internal structures of the terrestrial planets. Earth has an iron core, approximately 1/3 of its total mass. Venus is probably similar to the Earth, although because there's never been a seismograph landed on the surface of Venus, we don't really know. It is known that Mercury has an iron core that makes up perhaps 70% of its total mass, and Mars has a somewhat smaller iron core than the Earth and probably Venus. And so one of the questions in terrestrial planet formation is, how is it that our own solar system ended up with a diversity in terrestrial planet internal structure, which we're able to observe? And again, in the solar system, we can land things like on Mars, we can land seismographs, and we can actually study its internal structure in very high detail. That's not possible for exoplanet systems. So as people in this meeting already know, in exoplanet systems, if the system is observed to transit, then the depth of the transit is related to the ratio of the radius of the planet to the star squared. This is an example of the difficulty of the technical problem in precisely measuring transit depths related to terrestrial radius planets around solar-type stars. It's a very small decrement. And to turn the observable, that is the transit depth, into the desired physical quantity, the radius of the planet, one needs to know the radius of the star. And these stellar radii in these single planet systems are always inferred via some sort of stellar modeling. They are not measured. Likewise, if one wants to infer the mass of a terrestrial planet, one needs to gather some other information. This is an example Doppler curve for the Kepler-105 system. This is phased to the orbit of Kepler-105b. It's a mini Neptune with an orbital period of about 5.4 days. Again, the observables in this case are the eccentricity. The inclination comes from the transit. The Doppler semi-amplitude, orbital period, comes from either the Doppler velocities or the transit, but then one needs to know the mass of the star to get the mass of the planet out. And again, these masses come from stellar modeling. Also in this Kepler-105 system is the very interesting Kepler-105c. I'll come back to this planet later in this presentation. It has an orbital period of 7.13 days, and this Kepler-105 system is plausibly in a 4:3 mean motion resonance, and I'll also return to that topic later in this presentation. So what people typically do for exoplanets is we use the Doppler technique or transit timing to infer the mass. We take the transit observables and use the radius of the host star to infer the planet radius, and we put them in diagrams like this, where planet mass is on a linear scale on the x-axis and planet radius is on a linear scale on the y-axis. I've also here plotted as solid black points the solar system terrestrial planets. And then the four curves you see are the relationship between mass and radius for four different compositions. Now, what people do is they put the mass and observed masses and radius of terrestrial planets into this diagram and try and interpret them. So what I've done here is I went to the NASA Exoplanet Archive. I downloaded all of the masses and radii that had been published for the planet Kepler-10b. And there is dispersion, as you can see. And in particular, this analysis to analysis systematic dispersion is significantly larger than the quoted random uncertainties in any individual calculation. To emphasize that systematic uncertainties are the main issue in studying a population of terrestrial planets with the goal of understanding the population's internal structures. So there was an important contribution to this area by Vartan Adiabekian and his colleagues in 2021, where they homogeneously measured the iron metallicities of the host stars of planets, terrestrial planets, where the mass and radius were measured with enough precision that it made sense to talk about what their internal structures might be. Now, one limitation of the Adiabekian study is that while they homogeneously measured the metallicities of their host stars, they did not then use those stellar parameters to update the stellar masses and radii that were used to interpret the transit and Doppler observables. So there was even still a systematic in this analysis. And their conclusion was that if you study the population as a whole, there is a relationship between the iron metallicity of the host star, normalized to the solar metal mass fraction, to a core mass fraction inference based upon the planetary mass and radius. But if they removed what they called super Mercury planets, that relationship went away. And so in this interpretation, there is a relationship between the iron content of a host star and the mass radius-based core mass fraction of the terrestrial planets that might orbit it, but only in an increased incidence of supermercuries. And I should say, Brinkman et al. Have also studied this problem. We've already seen examples of that. They reached a similar conclusion to what I'm about to tell you. So what have we done? So we solved that limitation of the Adiabekian et al. Study, where we simultaneously used the spectroscopic stellar parameters and the stellar modeling to generate a physically coherent set of effective temperatures, log Gs, and metallicities that we also then used when we were calculating the stellar mass and radius. And we fit everything all at the same time to ensure there were no systematics relative to how the fitting was done, and also that the answer that came out was physically consistent with stellar evolution. Once we had those updated stellar properties, we used them to update the planetary masses and radii in a way, to the extent possible, remove some of the systematics I was referring to in that example of Kepler-10. So our conclusion is here on the left, juxtaposed with the Adiabekian result, which I've already shown. So this is the same diagram, but we find that the relationship between host star metal mass fraction and the core mass fraction we infer based upon the updated masses and radii of these planets persists independent of the existence of a population of supermercuries. So in fact, we only find one planet, Kepler-107c, that is a supermercury type planet. I should say that anything that's below this line 0 is inconsistent with the existence of a core. That is, anything below this horizontal line has a composition that is something other than 100% rock, that's less dense than 100% rock. We find that the two most metal-rich host stars in our sample have the two lowest density planets in our sample, and I'll revisit that point in a moment. Another innovation from our study is that we didn't just use our own high-quality spectroscopic stellar parameters. We also used the high-quality spectroscopic stellar parameters that were made available as part of SDSS4's Apogee 2 Data Release 17, and also the very high-quality stellar parameters that have been published by John Brewer and his colleagues over the last several years. And the conclusion is the same. So the statistical significance is lower here on the Apogee side because of small number statistics. In the John Brewer photospheric stellar parameters, we also obtain a significant relationship between the iron mass fraction of a host star and the core mass fractions of the terrestrial planets that orbit it. Now, also you see there's this other population that I've plotted in blue, which also seems to be low density. And I'll tell you about that in just one moment. So we can put our updated planetary masses and radii into these mass radius diagrams. For those of you who have expertise looking at these, you'll note that this is somewhat cleaner than these diagrams often can be. Often they also include planets with much less precisely measured masses and radii. What you can see here is that most of the planets in our population are consistent with the composition of the Earth. Kepler-107c, the supermercury planet that I've already called out, is different. Kepler-36b is different. Kepler-36b is in a mean motion resonance. I'll get back to that concept in a moment. And WASP-47e and 55 Cancri e are different. They're low density. These are the two terrestrial planets that orbit the most iron-rich stars in our sample, and they don't fit this pattern. These results are the same if we look at the photospheric stellar parameters from Apogee DR17, or if we look at John Brewer's work, this time also adding Kepler-105c, this planet system that I already called out, also in a mean motion resonance. So mean motion resonances were actually predicted to be the general outcome for systems of low-mass planets before Kepler's discoveries. One of Kepler's major discoveries in planetary demographics was that this is not the case. Planetary systems of low-mass planetary systems are not, in general, in low-order mean motion resonances, even if they might be close to mean motion resonances, as you can see in these two bottom panels. Now, it's actually quite challenging to know for sure whether or not a particular planetary system is in a mean motion resonance. And so what's done most of the time is to say this is a system that fits some heuristic, which is indicative of the planetary system being in mean motion resonance. So now if I treat the two planets in mean motion resonances in our sample as a distinct population, they have a systematically low mean core mass fraction, independent of the way the photospheric stellar parameter analysis was done. And this is in contrast to the rest of the planets in the sample, which are consistent with an Earth-like composition. Likewise, if I now talk about 55 Cancri e and WASP 47e, these ultra-short period planets orbiting very metal-rich stars, which have multiple giant planet external companions, they seem to be qualitatively different than the rest of the terrestrial planet population. And in fact, our interpretation of this qualitative difference, that is, why do they fall so far away from the relationship between host star metallicity and core mass fraction, is because they're qualitatively different. We believe the best explanation for 55 Cancri e and WASP 47e is that they were once the cores of a mini Neptune planet that has now been tidally disrupted due to many, many cycles of eccentricity excitation from its external giant planet companion, which leads to damping of eccentricity in the interior of the planet, removing orbital energy from its orbit, eventually bringing it close enough to its host star to be tidally disrupted, perhaps in a similar way to what Eve Lee was telling us about in her review talk. We're also able to investigate the possibility of a distinct population of supermercury planets that Adiabekian suggested. So we find no evidence for a distinct population of supermercury planets, but we find an occurrence of about 4%, which is fully consistent with the occurrence of Mercury-type planets, that is, high-density terrestrial planets in the solar system. So while the solar system has 1 in 4 of its terrestrial planets with this high-density property, it's a relatively small sample. And so the 1 sigma range in the occurrence estimate overlaps with the 1 sigma range of our occurrence estimate for our population. So in conclusion, the cores of terrestrial mass planets increase with host star metallicity. This is not a consequence of the existence of a distinct population of supermercuries. Terrestrial planets in mean motion resonances are less dense than the rest of the terrestrial exoplanet population. If you see a planetary system in a mean motion resonance, the usual interpretation is there was experienced convergent migration, and we advocate that this convergent migration took place over a long enough distance scale that these planets actually moved from a part of the disk where there was a lot more water, such that approximately 10 to 20% of their bulk composition is water. Again, 55 Cancri and WASP 47e are significantly less dense than the rest of the exoplanet population, and we argue that they are the cores of now tidally disrupted mini-Neptunes. Thank you. I'll take questions.
Thank you. That was enlightening. Let's start with Angarat over there.
Hi, thank you for this really interesting talk. So I just wanted to ask about these two planets that are significantly less dense that you're mentioning. If I'm correct, on the mass radius diagram, they were the ones, you know, with the highest sort of radii relative to the sample. And I was wondering exactly how you defined this sample. Like, is there a chance that, you know, in some parameter space, they're above the radius valley and we might consider them to still be hosting envelopes and thus different?
The sample was from, there's some echo. Should I still answer? Okay, the sample was from our colleagues Diana Valencia and Michael Plotnikov. They had an analysis where they rounded up all of the terrestrial mass and radius planets that had precise enough mass and radii that it made sense to think about them in this way, and that's the sample we used. So this was a sample in Plotnikov and Valencia 2020. And I should say that 55 Cancri and WASP 47e are both so hot and have been studied with enough detail to know that they do not have low mean molecular weight envelopes. It's still debated whether or not they have high mean molecular weight envelopes. They do not have low mean molecular weight envelopes.
Last question over here. Yes, that one in the middle.
Hi, I'm Nicole Gromek from McMaster University. So we talk about using the host star iron content to calculate core mass fractions, and there's been some progress in using additional abundances from the host star to place further constraints on terrestrial planet composition. What are your thoughts on that direction?
So we have done that as well. Those analyses are also included in this paper that's under review. I did not include them in this presentation, but the results are qualitatively consistent. That is that these abundance ratios in the host star do seem to have some value in understanding what the core mass fraction of the terrestrial planets are, but the interpretation is not as clear-cut as the mass radius-based core mass fraction, so I've chosen to focus on those. But I'm happy to share the draft of the paper with you if you want to see the details along the lines you just described.
That'd be great. Thank you.
Okay, before we go to coffee, our fearless leader has an announcement, but first let's thank Gavin again.